Good morning. Let us continue with the section on maxima and minima. We look at some more examples of these applications of derivatives. And today, look at example number 2. We are told to determine the height, or to find the height of a cylinder that has a maximum volume. This is inscribed in a sphere. So it's machine made from a sphere that has a radius capital R. Now with these questions, it's very important that you draw a sketch so you understand all the dimensions and how the two shapes go together. So what we have is a sphere like this, and then inside that sphere we have a cylinder that looks something like that. Okay, so the only thing we know in this question is that the radius of this sphere is capital R. So we want the volume of this cylinder to be maximum, and we know that the volume of the cylinder is given by pi r squared times the height. So you can see that this is an equation that involves two variables. There's r, which is first let me say net equals to the radius of the cylinder, and then we know that the volume of the cylinder is pi r squared times the height. So as I was saying, this involves two variables. It has r over here because we don't know what r is depending on how you make this cylinder. So you could make it longer, that means the radius has decreased. You could make it wider, the radius has increased, and so on. So that is a variable. And h is also a variable. Depending on whether you make it longer or shorter, the height will change. And whenever we have an equation that involves two variables, what we always want to do is rewrite one of the variables in terms of something that we know, so that it no longer involves two variables. So we go back to our sketch over here. What we can do is draw a right-angled triangle inside this sphere and cylinder. So this is the center of our sphere and also the center of our radius. So we can draw a right-angled triangle like that. So you can see that this goes from the center of the sphere to the circumference of the sphere. So that obviously makes it the radius of the sphere. Okay, and the radius of the sphere is capital R. Okay, now this one goes from the center of the cylinder to the body of the sphere. So this is half of the diameter, so this is the radius of the cylinder. So we call this one small r. And because this is the center of the cylinder, that means the distance from there to there, as well as from there to there, are the same. And we know that this distance here is the height. So that means this, if we call this part here height, then obviously the height of the cylinder capital H is going to be 2 times small h, okay, because this is the halfway point of the cylinder. Okay, so now that we have everything, so remember this capital R is fixed. That is given to us in the question. It is fixed, even though it's not stated as a number like 5 or whatever, because they say it's capital R, it is fixed, so you can take it as a constant. Now looking at this right angle triangle that we draw, we can form a relationship between capital R, small r, and h. And the relationship we form is that r squared is equal to small r squared plus h squared. This is by Pythagoras. Okay, so like I said, this equation over here involves 2 variables. So we only want one variable, and the variable we want is h because that is the one we're trying to maximize. So what we can do is rewrite this one or use this one to come up with another equation that involves h. Okay, so doing that from this equation here, we can say that r squared is equal to big R squared minus h squared. And keep in mind, this is a constant, okay? So it's fixed, it's not a variable. So then I substitute this equation in there. So I have that the volume of the cone is equal to pi times r squared. Now instead of using the little r, which is a variable, I use this formula here, which is a constant. So this gives me r squared minus h squared times the h. And now what I have over here, this has only one variable. And the variable that it has is h, which is what I wanted. Okay, so we can multiply this out and write it nicely because we have to differentiate it. So VC, that's the volume of the cylinder. It's the only volume we're calculating, so we need not distinguish and say VC, but why not? This is pi times capital R squared times h minus pi times h to the power of 3. So we're looking for the maximum. So we need to differentiate. So VC prime or dV dH, we're differentiating with respect to h. This is pi r, capital R squared minus 3 pi h squared. And then we know that at the maximum, the first derivative is 0. So at the maximum, VC prime is equal to 0. So we will equate this to 0 and then solve for h. That will tell us what the height must be for the cylinder to have a maximum volume. So doing that, we have 2 pi capital R squared minus, did we differentiate it? Yeah. Okay, so I'm missing something. I have h here. Okay, all right, doesn't really matter. Okay, in the end, we're looking for capital H, not small h. How did I get to h? I said it's from the center, if this is the center, then obviously it's halfway of the top and the bottom. So if the bottom is half and the bottom is h, so it means the whole height, this capital H that I'm looking for, is double of that h. That's where I got it from. Okay, so continuing. Okay, so we have 2, let me just see, I substitute pi. Okay, I see what I did wrong here. Okay, my formula is not correct. So here, this should be capital H, not small h. The reason this is capital H is because capital H is the height of the cylinder, not this one. Okay, too many big and small letters. Okay, so here I shouldn't have small h, I should have capital H, but capital H in terms of small h is 2h. Okay, so this is 2h. Let's fix that. Okay, let's see, right. Okay, so now we can multiply out, and what we have is 2 pi small h r big R squared. So 2 pi h big R squared minus 2 pi small h cubed. Okay, I think now it's fine, right? And then we differentiate as always because we want to find the derivative. So the derivative over here, we remember we are differentiating with respect to h because r squared is a constant. So this is just 2 pi r squared minus 6 pi h squared. Okay, and then this is the one that we will equate to 0. So let me just copy it. So we have 2 pi capital R squared minus 6 pi h squared is equal to 0. Then we can solve for h, can divide by 2 pi throughout first. So we get r squared minus 3 h squared is equal to 0. So this means that h squared is equal to r squared over 3, and h would be plus or minus the square root of r squared over 3, but because h is a height, we cannot have a negative height, so this is just r over the square root of 3. Okay, so key thing with this question and with a lot of questions in the exercise is your drawing must be correct. So there's no drawing given to you in the question. You must draw it accurately. You must be able to see all of these things and then apply your previous knowledge like Pythagoras, the volume of a cone, and so on. Okay, so if you have a cylinder with radius r and you want to find the maximum you want to inscribe a cylinder in that sphere so that that cylinder has a maximum volume, all you need to do is take the radius of the sphere, divide it by the square root of 3, and then that will tell you what height you must make that sphere. And then from there you can make your sphere. Okay, then number 3, we are told that a battery has an EMF of E volt and internal resistance of R ohm, and is coupled to an external circuit with resistance capital R ohm. Then the power over the terminals of the battery is given by this. So we have this formula: P is equal to R E squared over capital R plus small r squared. So here E and small r are constants. You can see this is a constant, that is a constant. So this is a function in terms of capital R. Then we have to find in terms of find R in terms of find capital R in terms of small r when P is maximum. So when P is maximum, obviously we just have to differentiate, equate to 0, solve for R. So we find dP dr. So we have to use the quotient rule. So that is the denominator as it is, multiplied by the derivative of the numerator, and then we subtract the derivative of the numerator, the derivative of the denominator rather, and then multiply by the numerator as it is, then divide by the denominator squared. Okay, so that is the derivative, and because we want the maximum derivative, so at the maximum, dP dr is equal to 0. So we can say that this whole thing here is equal to 0. So we can multiply the denominator out. So we have capital R plus small r squared E squared minus 2 R plus small r RE squared is equal to 0. And then we can divide by R, big R plus small r on both sides. The question is in your book. It's a very long question, so you can copy it from there. Let me see, somebody else said something. Somebody says mwene, says half of the whole h. I don't know what that means. Okay, then again we can divide by r, big R plus small r squared. You can see this bracket is common. So we will have R plus R E squared minus 2R E squared is equal to 0. I should have just also divided by E squared throughout, but you can still do it here, and I don't even need the brackets anymore. So I have big R plus small r minus 2 big R is equal to 0. So this leaves me with R minus R plus r, small r is equal to 0, and this means r is equal to capital R. Well, I should say it nicely. Big R is equal to little r, because big R is the variable here, and this is the constant. So usually, even though they mean the same thing, like when we're solving x is equal to 2, you can say 2 is equal to x, which is correct, but usually we like to leave it as x is equal to 2. So this is our variable. So this one here includes a lot of letters, but nothing too complicated or nothing that you really have to interpret, because it is just differentiating, equate to 0, and then you solve. Okay, then let's go to exercise 1.7.2. We'll do the odd numbered questions. Let's see how many of those we can do today. That is on page 33. So this is exercise 1.7.2. We start with the first one. We are told that the cost in rands per meter length of an electrical cable is given by C is equal to 110 plus 500 x squared over x. And x is the diameter of the cable in centimeters. Now we have to find the diameter of the cable with a minimum cost and the minimum cost per meter. So we have to find the diameter when the cost is minimum, and then actually work out what the minimum cost is. Okay, so again, this one pretty straightforward. Find the derivative, equate to 0, check that it is a minimum, then find the minimum cost diameter, and then the minimum cost itself. So we need C prime. So here, first of all, we can rewrite this as 110 over x plus 500 over 500x. Okay, so the reason I do that is because differentiating this, I think, is easier than using the quotient rule over there. You can still use the quotient rule to differentiate that. Your answer will be exactly the same as mine. Okay, so we differentiate this one now. We get minus 110 over x squared plus 500. And we say that we equate this to 0. So at the minimum, C prime is equal to 0. So we say minus 110 over x squared plus 500 is equal to 0. Then we solve for x. This means that 500 x squared is equal to 110. So x squared is equal to 11 over 50, and this means that x is equal to plus or minus the square root of 11 over 50. Now remember, x is the diameter, and because diameter is a length, we take x equal to the positive square root of 11 over 50. Now we want to check, is this in fact a minimum? Because there's two of them. One will give us a minimum and a maximum theoretically, but we know we're talking about realistic things that you can touch. It cannot be negative. So we want to check that it is a minimum. We use the second derivative. So C double prime, we just differentiate this one over here. So we have 220 over x cubed. and then we substitute this value there. Okay, I don't need to actually work out the value. I can tell that my answer is going to be positive because my numerator is positive. I'm substituting a positive x, and when I cube a positive number, my answer is positive. So I'll have positive divided by positive, my answer will be positive. But just to show, double prime of the square root of 11 over 50. This is 220 over the square root of 11 over 50 to the power of 3, and this is greater than 0. And we know that when our second derivative is positive, then we have a minimum. So therefore, x equal to the square root of 11 over 50 is, or gives us a minimum. Minimum cost, which is what we want. So we can say that the diameter is square root of 11 over 50, and to 3 decimal places, this is 469 centimeters. So that was the first part. It said find the diameter that gives a minimum cost. And then now we have to work out the minimum cost itself. So the minimum cost, we just substitute this value x into the original equation for C. So this is 110 plus 500 square root of 11 over 50 divided by, this is squared by the way, over square root of 11 over 50. So I'm just substituting it into this formula here for the cost. And doing that, get 469.04. So remember, for money, we like to leave it to 2 decimal places. Then you can write a sentence. The minimum cost is, here it was in rands, but I suppose they are equal. Right, so that was number 1. And number 3, we are told that, let's see it. Number 3, we are told that the total area of a sheet of paper is 20 centimeters squared. The margins at the top and bottom are 1 centimeter on 1 centimeter, and on the sides 3/4 centimeters in length. What must the dimensions of the paper be so that the area between the margins is a maximum? So again, with these questions, draw a sketch so you understand what it is you are working out. So we are given, this is number 3, we are given a sheet of paper like this. And as you know, all our papers have margins. So we put margins like this. Something like that. So the red area is the area where you can write, I suppose. And we are told that from the top, this length there is 1 centimeter. So that's also 1 centimeter. And then on the sides, we have 3/4 of a centimeter, like that. Okay, now we are looking for the dimensions of the paper so that the area between the margins is maximum. So we don't know what the dimensions of this paper are, but we know that the paper is a rectangle. So this is X and that is Y over there. Okay, then we can come up with our equations from there. Okay, so we know that our area is given by length times breadth. So this is just x times y. And in the question, we are told that this paper has an area of 20 centimeters squared. So before you make the paper, you know you want it to be 20 centimeters squared. So this is equal to 20. And now the area that you're looking for is the red area over here. That is the area that is between the margins. So here you have your margins. So the area between the margins is this one over here. So this red area is the one that you're looking for. And the equation of this, or the equation of the area of this margins would be it's also a rectangle, as you can see. So instead of x times y, you would say x times 3 over 4, sorry, x minus 3 over 4, and then minus 3 over 4 again. So that is your length. So you have x minus 3 over 4 on the left, and then you subtract it again, or times 2. And then from the top and the bottom, you subtract this 1 and that 1, so it's y minus 1 minus 1. So minus 1 minus 1, and this is the area that we are looking for. So this is maybe area of the paper, and this area here is the one that we're looking for. So we can simplify this, and then we have x minus 3 over 2, y minus 2, this is equal to a. Okay, so this is the one that we are trying to maximize. Okay, so we're trying to maximize it, but you can see it has two variables, there's x and y. So we need to replace one of the variables in terms of a constant, so that, or in terms of the other variable, so that we can differentiate it. So that leads us back to this equation over here. Since we know that x times y is equal to 20, from here we can say that y is equal to 20 over x. Okay, so if we know that y is equal to 20 over x, we can now substitute it here, and then you can see our equation A will be in terms of x only. So we have A is equal to x minus 3 over 2, and instead of y, we say 20 over x minus 2, and that is our equation. And now we want to maximize or work out what x is at the maximum. So we would have to differentiate. You can, if you want, multiply out and then differentiate, or use the product rule here. I used the product rule. So a prime, this is the first bracket as it is. So this is x minus 3 over 2, and then you multiply by the derivative of the second bracket, which is minus 20 over x squared. And then the second bracket as it is multiplied by the derivative of the first one. The derivative of the first one is just 1. So this is just plus 20 over x minus 2. Okay, and now we would multiply out our brackets, equate to 0, and then solve. So this is minus 20 over x minus 30 plus 30 over x squared plus 20 over x minus 2. Then you can see that these two cancel out. So this is just 30 over x squared minus 2. Okay, so that is my derivative, and we say that for maximum area, we solve or find a prime equal to 0. So we have 30 over x squared minus 2 is equal to 0. This means that 30 minus 2x squared is equal to 0. And this means that x is equal to plus or minus the square root of 15. And again here, because we're talking about length, something tangible, we must take x equal to the positive square root of 15. Okay, again, check that this does in fact give you the maximum, and to do that you use the second derivative. So our second derivative, a double prime, we just differentiate this. Go back to this, or
yeah, it's fine.
okay, so a double prime, we differentiate that and we get negative 60 over x squared. So we would substitute square root of 15 here, but I can see my numerator is negative and denominator will always be a positive number. So whatever my denominator is, the answer will end up negative. So even without substituting, I can see that my answer will be negative, and a negative second derivative means we have a maximum. But then we substitute a double prime of the square root of 15. This is negative 60 over the square root of 15 squared. This is negative 4, and negative 4 is less than 0, and therefore we have a maximum. We knew we would get a maximum, but you must show that this is in fact a maximum. Okay, so now we want the dimensions of the paper, or of the margins. How is it phrased?
Sorry.
Oh, want the dimensions. Somebody's saying something, but I can't hear them.
Yes.
Yeah.
Shouldn't it be minus 60 divided plus cube?
How did you get plus 2?
Because are we not differentiating with that, the first derivative?
This one, 30 over x squared minus 2.
So shouldn't it be, was that the second derivative, shouldn't it be minus 60 to over x to the power of 3?
Yes. Is it? Why do I have this as squared? Should be to the power of 3. Yeah. Why did I write 2? It is to the power of 3. Let me just see. Okay, yeah, it is to the power of 3, but our answer will still be negative. It won't be minus 4. I don't know what it will be here, but it will still be negative because square root of 15 is positive. And let me just work it out now. Negative 60 square root of 15 cubed. Okay, so I'm getting negative 1.03. Okay. 3. Right, so it's still negative. It doesn't change the fact that it does give us a maximum, but you're right, the derivative, I didn't differentiate. I'll change that here. Okay. Yeah, I should have negative 1.033. Okay, so now we want the dimensions of the paper. So we must say it is this length and this height or something like that. And we know that x is equal to square root of 15. So y will be equal to 20 divided by x. So this is over 15. So we can then say the paper has dimensions square root of 15, which is 3.873 centimeters by 20 divided by the square root of 15, 5.164 centimeters. Okay, number 5. We are told that the length of the slope of a right circular cone is 8 centimeters, and we need to calculate the perpendicular height of the cone for a maximum volume. So again, you draw your cone like that, and you are told that this L over here, the slant height, is equal to 8, and what else? The perpendicular height, this height h over here, we don't know. That is what we need to calculate, but we do know that this is the radius, even though the length of the radius is not given to us. We need to work it out so that the cone has a maximum volume. So we know that the volume of a cone is pi r squared over height divided by 3. That is the volume of the cone. And looking at our diagram, we have a right angled triangle over here. We also know by Pythagoras' theorem that h squared plus r squared is equal to h squared. So h squared plus r squared is equal to 8 squared. And like with the example that we did, we want to replace one of these variables in terms of the other, and we obviously want to keep the h because that is the one we are asked to solve for in the question. So we make r squared the subject of the formula here. So we have r squared is equal to 64 minus h squared, and then this we would substitute it in there, which gives us v is equal to pi. Then instead of r squared, we say 64 minus h squared times h divided by 3. So we started with a formula for volume that is in terms of 2 variables, and then we rewrite it so that it has only one variable, and we can differentiate, equate to 0, and get our maximum height. So doing that, we can have 64 pi h over 3 minus pi h cubed over 3. Right, so now we differentiate. So we say v prime, this is equal to 64 pi over 3 minus pi h squared. Okay, then we know that at the maximum, v is equal to 0, so this means that 64 pi over 3 minus pi h squared is equal to 0. Can divide throughout by pi, so the pi's will cancel, and we have h squared is equal to 64 over 3. So this means that h is equal to plus or minus square root of 64 over 3. Then again, because we are talking about a tangible length, it cannot be negative, so we conclude that h must be equal to 8 over the square root of 3. So we want to test, is this in fact the maximum? To do that, we use the second derivative, v double prime. So this is our v prime. We differentiate this with respect to h. We get minus 2 pi h. Is minus 2 pi h. Right, and again, you can see I'm going to substitute h, which is positive, so my answer is going to be negative, and that already tells me I will have negative second derivative, which means it is a maximum. So v double prime of 8 over the square root of 3, this is minus 2 pi 8 over square root of 3. Whatever that value is, it is less than 0, and therefore we have a maximum volume when h is equal to 8 over the square root of 3. So we can say the perpendicular height must be when the perpendicular height is 8 over, I want to write it to 3 decimal places. This is 4.619 meters, which is what we were told to find. Okay, then number 7. Number 7, we are told that the lengths of two sides of a triangle are each 1 meter. Then we have to determine the length of the third side of the triangle when the area is maximum, and then we also have to determine what this area is. So here again, just draw your triangle like this. Now what we know is that these two sides are 1. We can have an angle over there, theta. This side x is what we want to work out. Okay, so this one you have to think a little bit, apply all your previous geometry knowledge in order to actually work out what we are given. Now we know that with any triangle, if you know the lengths of the two sides and the angle between them, the area is given by half AB sine C, where A and B are the two sides that make up angle C. So in this case, our area is a half times 1 times 1 times sine of theta. So our area over here is just sine theta over 2. Okay, so we can differentiate. We differentiate, we get cos theta over 2 divided by 2, equate that to 0, and that means cos theta is equal to 0, and then we solve. So remember, our area here must be maximum, and at the maximum the derivative is 0. So A prime, this is cos theta over 2, and we say that at the maximum, A prime is equal to 0. So this means that cos theta over 2 is equal to 0, which means that cos theta is equal to 0. So if cos theta is equal to 0, this means that theta is pi over 2, and that's the only value that it can be because this is a triangle. And we know that with a triangle, the sum must be less than, the sum of the angles must be 180, so we cannot have angles bigger than that, or even negative, because negative angles do not go into a physical triangle. Okay, so now that we know what our theta is, so this is 90, our triangle actually looks like this. So this is 1, that is 1, this is 90 degrees, and then that is x. So we can use that to work out what x is using Pythagoras theorem. Okay, so this means that we have a right-angled triangle. Okay, so x here is the square root of 1 squared plus 1 squared. This is the square root of 2. Just a moment. Okay, so we have square root of 2. That is the unknown side. We even asked to work it out. What number is this? Number 7. Determine the length of the third side. Yes, we were asked to find it. So the third side has length 1.414 centimeters, and then we were also asked to work out the area. Okay, we can also again test that this is the maximum. So let me just do it, because sometimes in the testing goes for marks, so it's always good to show it. So a double prime would be the derivative of cos theta over 2, which is minus sine theta over 2. So a double prime of pi over 2, this is minus sine of pi over 2 divided by 2, which is minus half, which is less than 0. Therefore, it is maximum, as we knew we would. And now we want the area. The area is a half times 1 times 1 times sine of pi over 2. This is just equal to a half, or 0.5 centimeters squared. And that is how you would do that one. So this exercise has quite a number of interesting questions. Some of them you really have to think about them when you're answering them. And it's very important to draw a sketch so that you understand what it is they're asking you to do. So try doing those, and we'll do the rest of the odd numbered questions tomorrow. And I think then we can move on to partial differentiation.